Okay, let's look at this little bugger. This is finding the extrema and the saddle points for a multidimensional function of the form y cubed plus 3x squared y minus 6x squared minus 6y squared plus 2. I want to get used to using the second derivative test in this particular problem. Now, in the function's domain is all real numbers in R2, and it's differentiable everywhere. So the only places to get extrema or saddle points is when the gradient is equal to 0. So the first thing we're going to do is we're going to determine the critical points. So we're going to take the gradient, we're going to determine that. We're going to take the derivative with respect to x. We get 6xy minus 12x, and then the derivative of 6y squared in 2, that's 0. And then the derivative with respect to y is the second component of the gradient, 3y squared plus 3x squared minus 12y, and again the plus 2 is gone because it's the derivative of a constant. Now the key to find critical points, the gradient must simultaneously equal to 0. And I'm going to rewrite the first component as 6x times the quantity y minus 2. And I'm not going to do anything to the second component other than, well, I could factor out the 3, but I'm going to leave it there. So what we see is that this first component could equal to 0 if x is equal to 0 or y is equal to 2. This gives us two particular alternatives. So we have if x is equal to 0, then we plug that in to the second or the first derivative with respect to y, the second component of the gradient, to see if x equal to 0, if there's any critical points there. If x is equal to 0, then I'm going to put fy of 0, y would equal to 3y squared minus 12y. And if we factored out the 3 and the y, we get that this could equal to 0 if y is equal to 0 or y is equal to 4. So we now have discovered there's a critical point at 0, 0, and there's a critical point at 0, 4. But we also have the case when y is equal to 2. If y is equal to 2, then the first derivative with respect to y of x, 2, so I'm going to plug in the value of 2 for y, so we have 3y squared, so we have 4. I'm going to factor out that 3, we should have done that originally. We have 4 plus x squared, then minus, remember we factored out the 3 here, so this is a 4 times 2, so we have minus 8, which simplifies down to 3 x squared minus 4. And we see that equals a 0 when x is positive 2 or x is minus 2. So that means we have critical points at 2, 2, and we have critical points at 2, minus 2, 2. So we have 4 critical points. Now the second part is we are going to classify using our second derivative test. Okay, so critical points we're going to classify using the second derivative test. So we need to find the second derivatives. Now fxx, if I look at just here, I have 6 times y minus 2. If I take the second derivative with respect to y, for this function right here, we have 6y minus 12. And then if I look at fxy, take the derivative of y after I've done the x or vice versa. If I take the derivative of this function with respect to y, you have just 6x, which would equal to, if you took the y component and took the derivative with respect to x, notice that would equal 6x. Now that is guaranteed to happen because this function is twice differentiable. Okay. Now what we're going to do for each critical point, we're going to determine this quantity fxy squared minus fxx and fyy. And if this quantity is negative, that would mean I have an elliptical contours, which I have a max or a min, and all I need to then determine is if both of these are positive or both of these are negative, determine if it's concave up or concave down. And if this quantity turns out to be positive, then we know we have hyperbolic contours, which means the critical point is a saddle. So we need to evaluate this for all four of our critical points. So we're going to start with 0, 0. If we plug in 0, 0, fxy is 0, and I get minus 12, and that means my d, in this particular case, is minus 144. That's less than 0, so we must have a relative extrema there. And the fact that fxx, if you look at fxx up here, the fact that that's negative means it must be concave down there in all my directions. So that means I must have a max value. And what is that max value? I can plug in my value of 0, 0 into this function, and I get a max value of 2 at 0, 0. Now we're going to do the same exact thing for the critical point at 0, 4. If I plug in x equal to 0, again the fxy is 0. If I plug in y equal to 4, this becomes 12, this becomes 12. And so I still get the overall sign of d is negative. It still equals minus 144. That's still less than 0. But the difference here is the fyy and fxx share the same sign, and they're both positive, meaning that it's concave up everywhere. It's like a little bowl there. And so it means I must have a min at this location. And if I plug in that min value back into plug in 0, 4 into this function, I'll be able to get that min value. And it turns out that min value is minus 30. And that happens at 0, 4. Okay. So now we're left off with looking at, I'm going to put these two critical points together. If x is positive, negative 2, fxy would either be 12 or minus 12. But look, it's going to be squared. So both of these would end up having 12 squared, so 144. And then if I plug in y equal to 2, notice that makes this 0, and it makes that 0. So I just get 144 minus 0. That's 0. It means that these are both saddle points. So I have saddles at positive, negative 2, 2. I have a min at 0, 4, and I have a max at 0, 0. Now, if you went to MATLAB or CalcPlot 3D and other different devices to be able to look at this, it's very hard to see the max value and the min value in the saddles because the function can grow really fast when you get outside of a small little box. But what I would advise you to do is if you want to look at these saddles, try to look at a computational domain that is around 2, 2. So maybe look at 1 to 3, 1 to 3, that box. Vice versa, same thing with 0 to 4. Look at between minus 1 to 1 and 3 to 5 to get that little region. You should see circular contours here and hyperbolic contours there.